efficiency of turbine, steam turbine, as the ratio between actual work output of turbine divided by isentropic work output, that is equal to H1 minus H2 divided by H1 minus H2 dash. This will be in the range of around 90%, that is 10% loss of work due to internal irreversibilities, friction. Similarly, isentropic efficiency of pump is defined as isentropic work input to pump divided by actual work input, that is equal to H4 dash minus H3 divided by H4 minus H3. It is also in the range of around 85 to 90%. Now let us do a problem given in 1998 GATE problem regarding the Rankine cycle. The problem is given like this. A Rankine cycle operates between pressures of 80 bar and 0.1 bar. The maximum cycle temperature is 600 degrees centigrade. If the steam turbine and condensate pump efficiencies are 0.9 and 0.8 respectively, calculate the specific work and thermal efficiency. Relevant steam table extract is given below. The table is given like this. Pressure in bar, respective saturation temperature in degrees Celsius, specific volume, Vf and Vg, obviously they are in meter cube per kg. Specific enthalpy, obviously they are in kilojoule per kg for saturated liquid water and dry saturated steam, that is HF. HFG and HG. All three were given. Then we have specific entropy S, that is in kilojoule per kg Kelvin, that is SF, SFG and SG. The data are given as corresponding to 0.1 bar, it is 45.84, VF is 0.00101, because VF would always be in the decimals of 0.001 followed by some numericals, because for water at any pressure specific volume is 1 by 1000, whereas VG is at this pressure VG is 14.68, HF is 191.9, HFG is 2392.3, HG is 2584, SF is 0.648, SFG is 7.5, SG is 8.149. Corresponding to 80 bar pressure, the saturation temperature is 295.1, VF is 0.00138, VG is 0.0235, HF is 1317, HFG is 1440.5. HF plus HFG is obviously HG, that is given as 2757. SF is 3.207. SG is SFG is 2.535. SG is 5.742. Here a point could be noted that if SF and SFG are given, SF plus SFG is SG. Similarly, HF plus HFG is HG at any pressure or saturation temperature. So, when you are talking about specific enthalpy, it is sufficient to give either HF and HFG or HF and HG. All the three don't have to be or need not have to be given. Similarly for entropy also. At a superheat table, from superheat table, it is given that at 80 bar, 600 Celsius, specific volume is 0.486, enthalpy, this is very important, 3642, entropy is 7.02, all in the relevant units. The solution to this problem could be given like this. First of all, let us represent the cycle, that is Rankine cycle, on temperature entropy diagram. Because machine efficiencies were given, 1 to 2 is actual expansion, 1 to 2 dash is isentropic or reversible adiabatic, 1 to 2 is actual with friction. Similarly, 3 to 4 dash is isentropic pumping and 3 to 4 is actual pumping with friction. Of course, 4 to 1 is heat supplied in the boiler and 2 to 3 is heat rejected in the condenser. Now, first of all, let us calculate what is enthalpy at 2 dash, from which I can calculate the enthalpy at 2. Equating entropies for 1 to 2 dash, because it is isentropic, S1 is S2 dash. S1 is given as 7.0206, that is corresponding to boiler pressure of 80 bar and superheat temperature of 600 Celsius. So S1 is equal to, what is S2 dash? SF plus X2 dash into SFG at boiler pressure of 0.1 bar. They are given as, SF is given as 0.6488 plus X2 dash into SFG is given as 7.5006, from which I can calculate the dryness fraction of steam after isentropic expansion. From which we can calculate enthalpy at state 2 dash. H2 dash is HF plus X2 dash into HFG at condenser pressure of 0.1 bar, which is given as, HF is given as at 0.1 bar is given as 191.9 plus X2 dash, which was calculated earlier just above, into HFG is 2392.3, from which H2 dash could be obtained in kilojoule per kg. Please fill the blanks after calculating. Then, using the isentropic efficiency of turbine, which is defined as actual work output, that is H1 minus H2 divided by isentropic work output H1 minus H2 dash. This efficiency was given as 0.9 in the problem. In this formula, H1 is nothing but H soup, that is inlet enthalpy corresponding to the turbine, that is given as at 80 bar and 600 degrees centigrade, it is given as 3642 kilojoule per kg. That is given in the problem. H2 dash is just calculated, that is also known. Therefore, efficiency being given, we could obtain what is the actual enthalpy of steam leaving turbine could be calculated in kilojoule per kg. Now, for pump, coming to the pump, isentropic efficiency of the pump is given as 0.8 in the problem, which is defined as H4 dash minus H3 divided by H4 minus H3. That is, for isentropic pumping, writing TDS is equal to DH minus VDP, S being constant, DS is 0, DH is VDP. Therefore, integral DH, that is H4 dash minus H3 is integral VDP, which could be calculated as VF at 0.1 bar into pressure of boiler minus pressure in the condenser, Vf at point 1 bar is given as 0.00101 into pressure in the boiler is 80 minus 0.1. They are in bar, we have to convert into the kilopascal because 1 bar is 100 kilopascal. From this we can calculate isentropic pump work, that is H4 dash minus H3. Therefore, specific work output is equal to actual turbine work output minus isentropic pump work input. This is also actual, which is calculated as H1 minus H2 minus H4 dash minus H3, that is isentropic pump work divided by efficiency of the pump. This gives the specific work output of the cycle in kilojoules per kg. Then heat supplied in boiler is equal to H1 minus H4. The H4, that is enthalpy of water leaving pump, is equal to H3, that is enthalpy of water at condenser pressure, HF at condenser pressure, plus pump work input, that is HF at 0.1 bar plus, which was calculated pump work above, that is H4 dash minus H3 divided by efficiency of the pump. This gives the enthalpy of water leaving the pump, that is H4. Having calculated heat supplied in the boiler, that is H1 minus H4, we can obtain thermal efficiency of the Rankine cycle by taking machine efficiencies into account, is given as net work done per kg, which is also known as specific work, divided by heat supplied per kg, that is specific work done, which we have calculated, divided by heat supplied per kg. It will be approximately 35%. There is a usual range of Rankine cycle efficiencies. Now let us do another problem regarding the steam turbine given in a GATE 1999 problem, which is given on steam turbines. The problem is given like this: an adiabatic steam turbine receives dry saturated steam at 1 meganewton per meter square and discharges it at 0.1 meganewton per meter square. The steam flow rate is 3 kg per second and the moisture at exit is negligible. If the ambient temperature is 300 K, determine the rate of entropy production and the lost power. The steam properties are given in the table as pressure, that is the saturation pressure of steam. First column is meganewton per meter square. The respective saturation temperature of steam in degree centigrade, saturated liquid enthalpy of water in kilojoule per kg, that is HF, dry saturated steam enthalpy, that is Hg, in kilojoule per kg, the saturated liquid entropy SF is given in kilojoule per kg Kelvin, the dry saturated vapor entropy Sg is given in kilojoule per Kelvin in the last column. The data is at 10 meganewton per meter square, saturation temperature is 179.9, HF is 762.8, Hg is 2778.1, SF is 2.139, Sg is 6.586, corresponding to 0.1 meganewton per meter square. Saturation temperature is 99.6, HF is 417.5, Hg is 2675.5, SF is 1.303, Sg is 7.359. This is a table given along with the problem. The solution to this problem is given like this. First of all, let us indicate the expansion of the steam in the turbine on temperature entropy diagram or two-phase diagram of steam. He has given the turbine is receiving steam at a pressure of 1.0 meganewton per meter square. Please correct in the table that the table is given corresponding to 1. It's not 10 there. Please correct the previous table. That in the table it is given as 10. Please correct it to 1 meganewton per meter square because the steam is supplied with the turbine is supplied with steam at dry saturated corresponding to 1 meganewton per meter square. And it is discharging to a pressure of 0.1 meganewton per meter square. The steam actual expansion is not isentropic because if it is isentropic, the exit steam would have been wet. But actual expansion should be 1 to 2 because it is given that x2 is 1. Moisture at the exit of the turbine is negligible, which means dryness fraction at state 2 is 1. If the expansion had been isentropic, like 1 to 2 dash, the dryness fraction of steam at exit of turbine is less than 1. But Actually, the steam is leaving the turbine with dryness fraction of 1. It means the expansion is not isentropic, that is, there is friction, internal friction or irreversibility during expansion. So there is entropy generated. As we have shown in the figure, the entropy is always generated. So entropy is generated in the system due to irreversibility. Delta S, that is entropy generated per kg of steam is equal to S2 minus S2 dash. S2 is nothing but Sg, because this point is on the dry saturated vapor line, Sg at 0.1 meganewton per meter square, which is given in the table as 7.359 kilojoule per kg Kelvin. Whereas S2 dash is equal to S1, because 1 to 2 dash is isentropic, which is nothing but Sg at 1.0 meganewton per meter square, corresponding to which from the table it is taken as 6.586. Please correct in the table that it is not 10 meganewton per meter square. The first column, first row, it is not 10, it is 1.0. That is the pressure of steam at the inlet of the turbine. Therefore, delta S is equal to 7.359 minus 6.586 kilojoule per kg Kelvin. This is the entropy generated per kg of steam. Therefore, rate of entropy production is equal to mass flow rate of the steam into delta S in kilojoule per kg Kelvin. Therefore, rate of entropy production, that is entropy generated per second, is equal to mass flow rate of the steam is given as 3 into 7.359 minus 6.586. This is kg per second. Delta S is in kilojoules per kg Kelvin. Kg gets cancelled. The resultant unit will be kilojoule per second Kelvin. This is the rate of entropy production. When we come to calculate the last power is also known as irreversibility function I, which is calculated as T naught, that is temperature of the ambient, into delta S of the universe. Last power is nothing but irreversibility function I, that is T naught, where T naught is ambient temperature or surrounding temperature, which is given as 300 Kelvin. Delta S of the universe is equal to delta S of the system plus delta S of the surroundings. But delta S of the surroundings here is 0. Why? Since turbine is adiabatic. Though no heat transfer between the system and the surroundings, between the turbine and surroundings, there is no heat transfer because the expansion is adiabatic. Therefore, delta S of the universe is nothing but delta S of the system, which we had calculated earlier. Therefore, last power is equal to T naught into 3 into, that is entropy generated within the system per second, 6.586. This is units are Kelvin into kilojoule per second Kelvin. K gets cancelled. Last power is 300 into 3 into 7.359 minus 6.586 kilojoule per second or kilowatts. This is the solution for the problem.